So, good morning, everyone. We were talking about spectroscopy and shielding. So, what we found is the ordering of the energy levels are first to a first approximation. People in chemistry or physics always say that. To a first approximation, the energies of the quantum states of atoms, the standing waves, are defined by n, z squared over n squared. So this is the overarching rule, and we can draw for the hydrogen atom, for instance, the energy levels just by putting the charge on the nucleus, the atomic number z squared over the principal quantum level n squared, and that gives us energies, and the transitions between them correspond to energies that we can express in terms of wavelengths of light, photons, and those specific wavelengths are emitted or absorbed by the atom. Then we looked at something interesting. We saw that once you put the next electron in, then all bets are off. We know the three-body problem can't be solved in a closed form. So, but we saw, interestingly, if you have a helium and it's a helium ion, so helium plus, just as you would expect, since it's one electron, you can calculate the ionization energy, how much energy it takes to separate the electron from the proton. And it is exactly z squared over n squared because it is a one electron system. Put the next electron in, and now you have to start accounting for the interactions between the electrons. And we found, interestingly, that the s electrons, so if you have this slightly excited state helium, one electron in the 1s, and the next electron up here in principal quantum level 2, that 1s electron virtually perfectly shielded the electron out here. And how do we know that? Because the ionization energy from the 2 level in helium is the same as from the 2 level in hydrogen. And the hydrogen has 1 electron. So there's 1 plus charge here. The helium, the 2p electron, is only seeing 1 positive charge instead of 2 here. So that electron perfectly shielded it's close to the nucleus, and that's true for s orbitals. S orbitals strongly shield the p and d orbitals. Even the 2s is a very good shielder because s orbitals, as you know, there's no nodes, so they can always have electron probability at the nucleus. There's no place where they can't be. So we sometimes say they penetrate all the way to the nucleus. So s orbitals have a special access to the nuclear charge, and they can shield the other orbitals. And we found that just disturbs the energies slightly. It has the most dramatic effect when you find out that the 4s will fill, as you're filling up, adding electrons and protons and going across the periodic table, you find that the 4s electrons appear in electron configurations before the 3d because they're slightly lower in energy. So this effect it gets very, very, very complicated, so we won't go into too much detail, but our idea of shielding is one that we should take home, especially that s electrons are very good shielders of p electrons. So we did where were we then? We did a chem quiz based on that, I think. Where's that? Here? Nope. Oh, poop. But we did this one. Oh, yeah, stop it. We did this one, and we looked at, well, we can't see. Darn it. we did this chem quiz, and we said, well, now I'm going to do one electron systems. And be very careful here. It's tempting when you see Li plus 2 to put plus 2 for Z, the atomic number. That's not the atomic number. Remember, go to the periodic table. This is lithium plus 2. There's 3 positive charges, atomic number 3. It's plus 2 because there's only 1 electron. So it's a 1 electron system. So be careful not to put plus 2 in for Z. It's plus 3 in for Z. And we found that this 4p electron, so principal quantum level 4, we talked about what is the ionization energy of that. And this is it's kind of a contest here. You're saying 1 positive charge here in principal quantum level 2, 2 positive charges in principal quantum level 3, and 3 positive charges in principal quantum level 4. So you're getting farther away, but increasing the nuclear charge. Which factor wins is what the idea was. And we saw that we could calculate them all. So 1 electron systems, this is the ionization energy. It's the energy to go from the ground state, or whatever state we put it in, up to n equal infinity, or completely separated, 0 in energy. N goes to infinity, energy goes to 0. So the ionization energy from any quantum level, 2, 3, or 4, can be calculated, and by putting in the appropriate 1, 2, or 3 for Z, and then we just essentially just calculate them just to compare them. And you found it takes 1/4 of a Rydberg, and we do this on the exam all the time. I don't like you to have to calculate a whole number and do all the exponents and units, so we just express things in terms of R or K or something that's just easier to write down. So another reason, another lame reason, is the software is bad at exponents. So the software that presents it to you is lame. But this is simpler and easier anyway. And we can see this is about 1/4 of a Rydberg to ionize. This is about a half, a little more than a half. That's a little bit less than a half a Rydberg to ionize. So even though this is way out in the 4p, principal quantum level 4, it still takes less energy to ionize the hydrogen in the 2p. So the charge on the nucleus won out in that case. Let's look at the atoms now. So what do you think about the atoms? Let's talk about that among ourselves. We're going to have atoms. So notice, now we have the atoms in the same excited state. The outermost electron is in the same excited state, but the other electrons are still there. It's the atomic instance. So talk about that among yourselves and see what you come up with. I will also come. Okay, let's see what you're thinking. Oh, you can keep talking for a minute while you enter your thoughts on that. Go ahead and vote on that one and see what you're thinking after that informative discussion. Forgot to show you the possible explanations for each one. So let's see what you're thinking. You are thinking many for C, and A also has some adherence. Let's see what the reasoning is. So now they're atoms. The energy is still something like z squared over n squared, but now we're going to say it's the effective nuclear charge. So why is that? Well, we take the case of lithium, and a minute ago when we did it, it was lithium ions, so there were 3 positive charges here and 1 electron out here. And that electron could see all 3 positive charges, so very strong attraction. And we saw it was quite hard to ionize, even though it was in principal quantum level 4. But now we're talking about, well, it's still in this excited state. It's still got an electron way up here in n equal 4, but 2 s electrons down there. So now it's looking back and it sees 2 electrons interfering with those 3 positive charges and shielding some of those positive charges. So now it looks more like, we said s electrons are great shielders of p electrons. So it looks more like closer to 1 positive charge. There's 3 pluses and 2 minuses, 2 electrons around it. It sees much like a 1 electron system. 1 electron system, but with only 1 positive charge. So now it does go exactly like the n wins. This is, all of them see about 1 effective charge, and that means the highest n will be the easiest to ionize. So I do this little approximate symbol. Z effectives are always just approximations, and I'll never ask you to calculate a Z effective. We could do it if we said, here's the ionization energy exactly. What does that mean? Give you this and say, well, calculate that if you know this. That's just a simple calculation. But we're not really interested in that per se. We're more interested in this general effect of s electrons being very good shielders of p electrons and being able to rank ionization energies. So this, very easy to ionize, only a 16th of a Rydberg to ionize that state. Now remember, got to be careful. Easiest to ionize. This is more energy to ionize. Okay? More energy to ionize, be careful, does not mean lower, higher in energy. More energy doesn't mean higher energy on the scale. If we plotted the energies, we would still say, well, I'm going to take the energies, and here it is. Here's, we'll just throw something on here. Here's 1/4 of a Rydberg worth of energy. And that is the energy of n equal 2 for hydrogen. If you said z squared over n squared for hydrogen, you'd get 1/4 of a Rydberg. These energies are this 16th of a Rydberg. So this is something like n equal 4, but it's a 16th of a Rydberg. That's up here. And a 9th of a Rydberg around here. So this is the energy state that the helium is kind of in. So this is n equal 3 for the helium, and this is n equal 4 for the lithium atom. And this is what I'm pointing out. More energy of ionization means lower energy level. I just want to point that out because we start saying more and less and bigger and smaller, and you're flipping it around. This requires more energy to ionize than this or this. So the lowest ionization energy is the highest energy level. And lowest and highest in the same breath kind of can lead to some confusion. All right? But keep that in mind. All these energies have a negative sign in front of them, right? 0 energy is the ionized state. So they're all lower than 0. And this number, 1/16 R or 1/4 R, that is that gap in energy. That's a change in energy, ionization energy. Okay? So try to keep that straight. It will show up, well, you're probably seeing it in the homework if you're already doing that homework. They all look about like a hydrogen atom, about like a 1 electron system. Okay? Oh, this, I love this. We better talk about this one too. For which atom does the plot depict the ionized electron energy versus light? So we're bringing two things together. This looks like the photoelectric effect. So I'm increasing the photon energy, and I'm trying to see where the electrons leave the atom. And electrons leaving the atom is an ionization. It's an escape from a potential well. So we're looking back at the photoelectric effect with our new knowledge of ionization, what ionization is, the escape from the potential well. So we remember that if we're talking about the photoelectric effect, we were describing how there's the positive charges on the metal attracting the electron, and we had to give the electron more than this much energy for it to ionize. And that was that energy right there. That's the amount where it's just enough to ionize. And then any more energy than that just goes into the kinetic energy of the electron as it leaves. So that's why the more photon energy you get, the more kinetic energy that you get. So which one of these depicts this if this is falling squarely in the ultraviolet region? So I wonder if we have hints for this one, because we can either give you some hints or we can show you something else. What are the hints? We'll do two things. We'll show you the hints. Let's start this one. So go ahead, you can start talking about it. I'm going to show you. I'll start it so it's on your phone or you're on your device so you can look at it, or you might have it in the notes so you can look at that. And then we'll give you some other information. The hints, if I could have the output of the output of the tablet up on top, and even more hints. Let's more information. Let's just go back to here and just remind you what those energy spacings look like. Okay, let's talk about that. Lots of information to talk about there. Let's talk about among ourselves. Okay, let's see what you're thinking with some time to think about that. I will go back to, if I can find it quickly. It's hard to see, it's that one. So this is what we're talking about. And the chem quiz is running, so let's see what your thoughts are on this. Go ahead and vote if you have not yet so far voted. We'll look at hydrogen and 2p is quite popular, and lithium, the next most popular. That makes sense. You might go to one extreme or the other. So we had, it's actually easiest maybe just to go back to that picture we had up there for you to look at. This picture, this is for hydrogen. And now it's for any one electron system with one proton. So this is one positive charge and one negative charge. You should be able to look at this and look at the ground state energy and kind of tell me what atom that is. Because you know the way to get minus R as the ground state, you know the ground state, the energies are minus Z squared over N squared R. The way to get N equal 1 to be minus a Rydberg is to have Z also 1. So you should be able to look at that and say that's hydrogen. That doesn't mean that helium doesn't have an energy level at R, and we know it does because 2 squared over 2 squared is also minus a Rydberg. But that would be N equal 2, and we're saying this is N equal 1. So this, you should be able to look at it and say that's hydrogen. But we also said that these three species, the hydrogen in level 2, N equal 2, the helium, it looked like a one electron system because it had that screening, that shielded nucleus, one electron down there. So it looks like a one electron system. And we already calculated the ionization energies. And we said the ionization energies, the hydrogen was actually the hardest to ionize in the atomic state. And the lithium up here in 4 was the easiest to ionize. And you can see it dramatically there. Lithium as a one electron system, lithium up here in 4, easy to ionize. The hydrogen was in 3, easy to ionize, and less than UV. We told you this gap is ultraviolet. So all these smaller gaps, and we've even drawn in color, are visible or infrared. So in our quiz, we can see hydrogen required the most energy to ionize, and we can see, even from principal quantum level 2, to ionize it, we've only gone 2 to 5, and it already requires ultraviolet. So more than ultraviolet and more to get it to ionize. For the helium acting like a one electron system in 3, less than ultraviolet, probably just barely visible or infrared, and level 4, probably just infrared radiation is enough to ionize it. Or near infrared. So very, very instructive process, and you know that's what I like to do. I like to give you a plot and ask you some questions about it, and you have to wrap that all together. You understand what this is. You understand what this means. Most importantly, you understood right there must be the ionization energy. That's how much energy it takes to ionize. And then beyond that, it's all gravy. The electron just gets kinetic energy from all the photon energy after that. But how would I do it? How would I do it on the exam? You know, who can predict what I would do? Anybody? I'd do something like this. Here's what the figure would be. Match the plot to the species. And you would say, oh, those are the ionization energies. And I can order them by ionization energy, can't I? So I would pick that. This went to 0, didn't. That's just because I drew it quickly. But think like, no, sorry, I was going to say think like me, very dangerous. You don't want those kind of psychiatric bills. Think like yourselves, but try to anticipate what I might put on the exam. Okay, so we like that. And there's the picture. Oh, I did the next to each other so we could see it. I could have just gone to this. Okay, can a photon of 30 nanometers ionize helium from its ground state? Now, here's something where we've given you some information, but it doesn't look like any useful information at a first glance. Number one, we're talking about helium, and like I said, you should recognize that this is not helium. Ground state is minus R. What's the ground state of helium plus the 1 electron system? Well, it's z squared over n squared, so n is still 1, but z is 2, so it's minus 4R. So way down here somewhere, minus 4R is the helium ground state. So we can already say that takes much more energy than this much energy to ionize. So we know it's more, but how much more? Well, this energy gap corresponds to about 120 nanometers. And what is that energy gap? Let me just, oh, I said we were going to do this in discussion. Well, I'm halfway through it, so let's just keep going. That energy gap is 3/4 of a Rydberg. You went from minus R to 1/4 R, so that difference is 3/4 of a Rydberg. So we know that photon energy corresponds to 3/4 of a Rydberg. But we also know it takes 4 Rydbergs to ionize helium plus. Well, 3/4 of a Rydberg is 120, but we asked about a 30 nanometer photon. And a 30 nanometer photon, how much more energy is that than that? It's 1/4 the wavelength. So 1/4 the wavelength means 4 times the energy. So this photon has 4 times this much energy, but that's still only 3 Rydbergs. So it's not enough. Okay? That's a very good problem. That's something I would put on an exam. I would do this. What else would I do? I would put this and this in the figure. And oops. And we would say, well, this, and we tell you which one of them, which one of it is. This one is this one is this one, and I would ask you which of these corresponds to 120 nanometers in energy. And that's an easy question. I wouldn't say it like that. I'd say, here's A and B, point nu A and nu B. And I would say you have 2 photons, 120 and 30, which could potentially correspond to which? And then that's easy, I hope. This is the high energy photon, this is the low energy photon. So that's the high energy photon, that's the low energy photon energy. Remember, I'm always trying to ask you the easiest thing about the figure. You guys always try to go to the hardest thing or wrap in all kinds of stuff. Try not to overthink what's in the figure. So that would be there. And then you could say, oh, well, go through all that whole calculation. You only have 3/4 of a Rydberg, but you could put 3R on here, and you could say, well, where does 3/4 of a Rydberg fall? Well, we're saying 3/4 of a Rydberg is the lower energy. That one is here. It's not quite an ionization energy, so that's some different species. So where would I put 3 Rydbergs? Well, it's bigger than that, and 4 Rydbergs is bigger than that. So if you really wanted to ionize helium, you're way out here somewhere at 4 Rydbergs of energy, and that corresponds to some frequency greater than 30 nanometer wavelength. And you could say, which one of these is the corresponding? If you know that one is 120 or something like that, you could arrange them. Anyway, you get the idea. Look at the figure, get the energies. I'm just talking fast here, wrapping 3 or 4 things together so it doesn't make exact sense, but you get the idea. Energies on this line correspond to photon energies. You know which is bigger and smaller, you know the easy things. You can talk of them relative to each other, like we could say this one is 30, or this one is 30. That means this one must be 120, or that one must be 120. So all those things are things that I would ask you to get from the figure and then apply to the system and talk back and forth. Okay. That's what we thought the answer was, not enough energy to do that. And I said I would do all this in discussion, so hopefully that's happening. So we can move on now to the next thing. And the next thing is, we're still talking kind of about our quantum mechanical structure of matter, the quantum nature of matter. We're going to continue to do that, but we're going to look now at the periodic table in particular. We haven't looked at it in too much detail, but this is the time, now that we're armed with all this quantum mechanical information, to look back at the periodic table. And this is important because you know that the periodic table, if you look at your old chemistry books, you'll see, or Google it online, the periodic table was developed before quantum mechanics. And how did they do it? If you look at your old chemistry books, you'll see like this lithograph of, you know, some old dude with a funny hat looking at a beaker. And that guy was doing the chemistry, and he noticed all of them communicated, and they noticed the chemistry of these elements was similar. They reacted in similar proportions with each other. So they were able to arrange the periodic table, not these, but these, and some of these. They could arrange them by just, let's put them in a column if they react with similar compounds in similar proportions. That's all they could figure out. But it got them to something strikingly similar to the modern periodic table. Could go write it there. But here's the fantastic triumph of quantum mechanics. You say to yourself, is this quantum mechanical description, you know, right? Does it bear anything to reality? Well, yes, it predicts ionization energies exactly. So yes, it's a good model for the atom. In fact, we said a couple weeks ago that it was the best mathematical model in physics, the one electron system, predicting exactly ionization energies. But there's more to that. this whole n, L, m sub L is actually reflected here. And that's a huge triumph of quantum mechanics to say, yes, it predicts this the same way that the properties of the elements would have predicted this. And you can see it. Principal quantum level is reflected in the rows. So n equal 1, hydrogen, n equal 2, lithium and beryllium, n equal 3, sodium, magnesium. All these are electrons in principal quantum level 3. And we see that to be the case. So it reflects n. Does it reflect L? And yes, it does. It reflects L as well, because there are 2 columns in this region of the periodic table. And if you have L equal, we call LS, so that, I probably write it down, that's L equals 0. So how many values of m sub L are there for L equals 0? One value, it is 0, yes. So there's one value of m sub L. So if we're just writing out the quantum numbers, so far, n, remember we write them in sets of 4, n is reflected. L, the value of L we think is reflected, and if it's 0, so let's just say let's say we're here, 2. 2, L equals 0 is possible for principal quantum level 2. What about m sub L? Is m sub L reflected there? It is, and here's why, because we just said the only value that m sub L can have if L is 0 is 0. That means one kind of orbital, one type of orbital, if I have L equals 0. So I'm talking about, from just this information, I'm talking about this, and I'm talking about an s orbital. There's only one of them, and I can have 1, 2 electrons in it. So I expect 1 orbital, 2 electrons, this to be 2 columns wide. S1, S2 is reflected right there. So an m sub s of plus or minus 1/2. This, I've described 2 electron addresses. Spin up, spin down, in an s orbital, and it can be any one of the s orbitals, because it's L that determines there's 1 orbital with 2 electrons, not n. So s is reflected here, the value of L. I can keep doing that. Same thing here. 1, 2, 3, 4, 5, 6. 6, there's room for 6 electrons here. And of course, that's because this block corresponds to L equal 1. So when we have L equal 1, what are the possible values of m sub L? M sub L goes from minus L to plus L in integer steps. So in that case, it's minus 1, 0, 1. 3 values of m sub L, that's the 3p orbitals. And 3p orbitals can have 1, 2, 3, 4, 5, 6 electrons. 2 electrons in each orbital. So that's beautifully reflected there. And you can keep going. D, there should be 5d orbitals because L is now 2. So m sub L has 5 values, 10 electron addresses across here. And then this block here represents L equal 3, the F orbitals filling. Okay? So, ginormous triumph of quantum mechanical all that N, L, and M sub L stuff is right in the periodic table. We didn't know it until we solved the quantum mechanical structure of the atom hundreds of years after this was proposed as the structure of a periodic table. And it was periodic because the properties repeated periodically. So with the mass of the element. I should point out something. How would you, what's a good exam question? Remember, sets of quantum numbers, N, L, M sub L, M sub S, are addresses for individual electrons. If I give you an N, L, an M sub L, and an M sub S, I've given you the address of one electron, the quantum numbers of one electron. And the address really just comes from these first three. If you want to talk about a location on the periodic table, the location on the periodic table comes from these three, and this M sub S is why you get duplicates of every address. You get 2 electrons can fit in each address. So you're talking about the N can kind of give you the street you're on. N gives you the street you're on. L gives you the house you're on, or the block you're on. Street, 2 different blocks on that street. And then M sub L gives you the house on the street. So you can get to this house on that street. M sub S just tells you there are 2 people living in that house. You have a spin up and a spin down, possibly. So the address of an electron, and we're really stretching the metaphor, but it's a place an electron can live around an atom. And we often just talk about the outermost electron. So it is the address. If you talk about this and you say, well, this argon there must have everything from the beginning. So argon must be 1s1, 1s2, 2s1, 2, 2p, 1, 2, 3, 4, 5, 6, 3s, 1, 2, 3p, 1, 2, 3, 4, 5, 6. I can say that the outermost electron it's in the 3p, and there's 6 of them. And from here, I can write that address. N is 3, P means L equals 1. M sub L, well, it's one of the 3s, 0, 1, minus 1. We don't make an exact connection between which P is 1, which P is 0, and which P is minus 1. We often say X, Y, Z too. But as far as the nucleus, the atom thinks it's got an atom, it's looking out at the orbitals. They don't have addresses. All the P's are equal as far as it's concerned. So whether this last electron is in Px, Py, P or Pz, or to write it with M sub L, we said minus 1, 0, 1, the 3 values of M sub L, the atom can't tell which one it is, and they're all equal energy. So it doesn't matter to us which one it actually is. So these 2 are very important, and then this one, we know it's one of 3, 1, 0, minus 1, but not which one. And here it's one of 2, either plus or minus 1/2. These 2 we don't know exactly, but those 2 we do know exactly. Here we have a choice of which one we just choose to label. So if you look at these 3, if you look at these 3p orbitals, 3p looks like there's 3 of them, -1, 0, and 1, or x, y, z, whatever you want to call them. We know that correlation isn't a good one, but there's the important part, there's 3 different ones. Same energy, though. So if you're looking at aluminum here, you really can't tell. Is it this one? Or this one? Or this one? It doesn't matter. All of those are identical, aren't they, in energy? So you can't get too specific. You can get the N and the L, but the M sub L you can't get, and the M sub S you can't get, because all of these are the same. All right? And notice, spin up or spin down, as long as there's no other electrons here, spin up and spin down are the same. Doesn't matter if the first electron to go in is spin up or spin down. There's the same energy until there's another electron there. And then it matters. There's another electron, then there'll be parallel spins. Okay? So all that beautiful information wrapped up in the periodic table. So now we can look at a few trends, and this is really relaxing stuff to talk about now. We're out of the nitty-gritty quantum mechanics, and we can just say, well, there are trends in the periodic table reflected in the organization of the periodic table. And I think you would easily guess, if you're talking about how big the atom is, if you go down a column, you're just going to bigger principal quantum level, n equal 1, 2, 3, 4. They get bigger, atomic radii get bigger. That's not a big surprise. As you go across, though, you might be surprised that here atomic number is increasing. You are getting a bigger nucleus, but the size of the atom decreases. And that's because you're adding electrons, and in general, you're adding electrons in the same principal quantum level. So you're adding all those in n equal 3. So you're going in the same region of space, but the difference between aluminum and silicon is silicon has another plus charge. So electrons in the same region of space, but more charge is kind of compressing that 3p orbital gets smaller and smaller and smaller because the nuclear charge gets bigger and bigger and bigger. Okay? So you can rationalize why the radii would decrease across a row, and you can see how beautiful that trend is. There are very few exceptions to that. Ionization energy, same thing. We have to remove an electron from a system. Does that have a trend? And we should expect, yeah, it probably has a trend because it depends on N and a certain extent on L. So we should expect a trend there. Let's define it. Ionization energy now is the gas phase. I didn't write gas phase, but we do ionizations in the gas phase to be consistent in the standard state, 1 atmosphere of gaseous molecules. Ionizing, so an electron comes off and you have the electron and the negatively charged electron. This is the 0 energy state compared to this is an ionization energy. And this one is it always positive or negative? Does it take energy or is energy released when that happens? Everybody should scream this out. If I have to pull the electron off, that takes energy, that's endothermic, okay? So all of these require energy. So this is the higher energy state. Even though we give it the number 0, it's higher than all the negative energy states. So this requires energy, endothermic. I don't know if I write that or not. Well, let's just see if I write it. Well, we give you some, so that's good. This is the electron affinity. The electron affinity is Well, let's say you had the atom and you want to know, does it accept another electron and become negative? What's the relative energy between those two? So this one we've been drawing all the time, ionization energy. Oops, don't write until you've pushed the button. This ionization energy we're doing all the time. Here's 0 in energy, ionized state. Down here there's some n equal, who cares, 3 state. That's the highest electron, highest energy electron. We're going to ionize the highest energy electron, the outermost electron. So that's where we've been talking, the 3p electrons, for instance. Ionize those. That is the ionization energy. So here is X, the atom, and here is X plus and an electron. That energy gap. And you know, if I were going to show it to you, I would show it to you like that, in a gap. Okay? And then I might ask you, well, write it for this one. And tell you that this one's endothermic, this is exothermic. Well, how do I arrange these? Well, I have one state here, X plus an electron. And this state, this is exothermic. So X minus must be down there. Okay? And that might bug you a little bit. You're saying, oh, the atom and an electron is less stable, is higher energy than the negatively charged. This is the more likely state. If you have a free electron and an atom, the lower energy state is for that electron to be on the atom, in many cases. That should make a little sense to you. The atom, the nucleus does have a positive charge, and we know it's not perfectly shielded. So it's neutral, but fluctuating in there. This electron can see there's a little positive charge there, and it's lower energy for that electron to be on the atom than free in space. So that we take home, and that's the picture you should expect to see, or might expect to see on an exam. Arrange them in terms of energy. And here are some of those energies. So ionization energies of sodium, potassium, rubidium, chlorine, bromine, iodine. Those are the ionization energies. And notice sodium is fine accepting an electron and going to Na minus. That's lower in energy. It releases energy when that happens. In fact, all of these are happy to accept an electron and go to their negatively charged state. Something you might not have expected, but there's the proof of that. So Karen, you can come out and show us this dramatically. So we're going to look at a couple of those. The metals, sodium, potassium. We're going to look at the metals, sodium, potassium, rubidium, cesium, francium, going down the periodic table there. And we're going to look at their relative ionization energies in kind of a unique way. We're going to put them in water, and they'll react with the water. They'll form hydrogen gas and this oxide of the metal. And what we're saying is, two things are happening: the ionization, and then the reaction of water to form hydrogen and these OH minuses. So we've broken this up into two steps. One step is just the one we know, ionization. That's the one we're interested in. Ionizations are also called oxidations. We'll talk about that later. Essentially, these electrons go find the water, and they make this hydrogen gas and this hydroxide ion. The formation of this hydroxide ion will change the pH of the water. We're going to talk about that next week too. So as this reaction occurs, we should see two things happening: hydrogen gas being released, energy being absorbed or released. It's not clear yet. We know this one requires energy. So if this one also requires energy, then the whole thing is endothermic. If this one releases energy, then if it releases more energy than that takes, then the whole thing could be exothermic. And we know we've done this before. We can take the equilibrium constants. We can add up the enthalpies. And I've already given you the hint. This reaction is exothermic. So is it more exothermic than this? So that the sum of them, if you add those two reactions together, I'm going to multiply this one through by 2. So I have to multiply that through by 2, add them together, and that's the reaction that's going to happen when Karen mixes the metal. And if this magnitude of this is more than twice that, so then we'll have an exothermic reaction. And this is what we'll be able to see. This one is the same for all the metals. So this releases the same amount of energy. We have to say, how much does this take away from that? How much? So a high ionization energy would make this reaction more boring, because high ionization energy means high endothermic, but the same exothermic. If it's easier to ionize, lower ionization energy, then it's more exothermic overall, and it'll be more exciting. So let's look at them in sequence, Karen. We get to see what? Sodium? Oh, we have lithium. Yes, let's see lithium. Cool. So we're going to start first column of the periodic table at lithium. And our thought is the easier it is to ionize, the more exciting the reaction. Or the harder it is to ionize, the more boring the reaction. So by the level of excitement, we can arrange these compounds in ionization energy and see what the trend is going down a column. Go for it, Karen. Should we bring the lights down? Or is it, so she's putting in, that's a clever idea. Karen is super clever. What she did there, she sprayed an indicator, acid-base indicator in there, so we can kind of see the hydroxides forming, because it'll change color too. She's smarter than me. Not surprising. So there it is, and there it is. Oh, that is so cool. So there's the lithium reacting and leaving a path of hydroxide ions in its wake. I love that. And you can see it's releasing, the bubbling is the releasing of the hydrogen, but it's pretty calm because this is taking up most of the energy, the ionization is. Okay, let's look at the next. Can we do that? Can we do it at the same time, or is that dangerous? So now she's going to take sodium, I guess. So here's sodium metal. Oh, a big chunk too. Excellent. There's sodium metal. There the reaction is starting. And we can already tell it's more vigorous. We can see more hydrogen gas being formed. Oh, it does. And it's out on the table, I think. Left the building. There it is. Flaming out on the table. That was exothermic enough to ignite the hydrogen that was being formed. So that one blew up. Karen is ready with her fire extinguisher. So that one has a lower ionization energy. This took up less of the of this reaction's energy. This is fun then. So we're going to go to potassium, and that must be even more energetic and a big healthy piece. I'm going to try from the top. Oh, and it immediately bursts into flame. Oh my goodness. Okay, so clearly and the funny thing is we're saying that's a lower ionization energy because it was taking away less energy from the exothermic. This is the endothermic part, this is the exothermic part. Excellent. Is that all we have? Yeah. So rubidium is a little harder to come by, and cesium. They're they have to be stored in glass ampules because they're so reactive that they do this reaction with just the air. Even those metals, can you show, Karen, you had the metals in beakers, right? Yeah, just bring a beaker out in front here. So the metals had to be stored under a hexane environment because they'd react with the moisture in the air. So they have to be stored under a hydrophobic liquid. So cool, that's a beautiful demonstration of that. If you go online, I wonder if I did this. I didn't. You can Google it. Kind of surprised I don't have it there. Oh, maybe we'll see it here. If you Google, sodium in water, you'll see a million of these demos. But then there's some crazy guys out there that are taking chunks of sodium and throwing them in a lake, and just the whole thing blowing up. So go look at that on your own time. So we saw ionization energies as we went down decreasing. These were taking less and less energy away from the exothermic part of that. So decreasing ionization energies. And we can also kind of rationalize that. You are getting bigger atomic radii going up, and there's the shielding going on. So the atomic radius is going up, and the outermost electron isn't seeing this huge increase in positive charge because you're getting more electrons too. So you just have this electron pretty far from the nucleus, getting farther and farther and farther and farther away, and seeing a pretty similar effective nuclear charge. So it's the getting farther away that makes it easier to ionize. And going across the periodic table, you kind of expect what you see here is this slight increase in ionization energy, and that also went with the trend. Those were getting smaller. Those were getting closer. Remember, these radii were getting smaller. Radii getting smaller, those electrons are getting closer, and you're adding charge. Because you're adding charge to the nucleus, those get harder to ionize as you go across. Harder to pull that electron off. Let's just talk through this one together. What is the ionization energy of chloride minus? This is a fantastic exam question. Oh, maybe we'll put it on there. Why is this such a good exam question? I'm asking you the ionization energy of chlorine minus. There it is. Cl minus goes to Cl and an electron. Have you seen that somewhere before? In the figure, Cl minus goes to Cl plus E minus. Have you seen that somewhere before? Well, do I show it to you? Let's just go back. Ding. Have you seen that before? The negative species going to the neutral species plus an electron? Yeah, right there. Except in reverse. So you know that energy. That energy to ionize this, you are ionizing that if you go in the reverse direction. You're taking an electron off, but you know that energy is the opposite sign of the electron affinity of chlorine. So you go find the electron affinity of chlorine, and you say it'll take plus 349 kilojoules to take that back off. It went down in energy when you added it. You're just going to take it back off and ionize it. So the reason that's a fabulous exam question is that could be there, and you would realize, oh, well, that's the opposite. I'm asking about the opposite of that. And you would put it on there. What's this one? Oh, that's probably just, don't do that. Do I not have power? It looks like I have power. Okay, so let's We're looking at that trend in ionization energy. This is the same plot, a little bit different, circles instead of squares. Let's write them down. Did I skip anything? Let's go back to the chem quiz. There it is. The ionization energy of chlorine minus is plus 349. We understood that. Some people somehow voted on that. Maybe that's from last time. That's an ionization energy. This is an electron affinity, and we were doing the reverse of that. Oops. So the reverse of that is the reverse of that, which is plus 349. Okay, there are those ionization energies again. Down, energy decreasing as you go down, and energy increasing as you go across the periodic table, and we understand what that is. Here are more of the numbers explicitly along with the electron configurations. And we've come right back to day one of chemistry. Remember we said, what is stable? And I don't like to use that word, and you don't hear me using that very often. The phrase I use is lower energy. Because all stable means is you're lower in energy than your neighbors. It takes energy to go anywhere else. That's what makes you stable. And that should make sense. You're stable because you don't want to move. Stationary because it takes energy to go anywhere else. So you are stable if you are low energy locally. And you've seen in your, probably when you took chemistry in high school, they said, oh, beryllium is right here, 2s2, and they said, oh, that's a closed shell, so it's stable. And that didn't mean anything to you, and it shouldn't. Because something on its own, you don't put the word stable next to. You look at the things around it and then say, stable, I have to compare to something. So just saying out of the blue, this is stable, doesn't help you, right? Stable with respect to what? Well, now you know. Look at beryllium. Here's beryllium. In order to ionize it, it takes energy. Okay? So let's write it down. I don't have any room. Okay, let's be fancy pants. Let's take this table and put it in a whiteboard. Okay, there it is. It's gigantic. Too big. But there it is. Let's erase all the markings on the board and look at that. That thing. Yeah, let's just get rid of that thing so it's not in the way. So there's our atomic properties. We're looking at beryllium here, and we're saying its ionization energy. Oops, gotta go back to a pen. Its ionization energy is here. So to do the reaction, beryllium goes to beryllium plus an electron. That requires energy. So here's beryllium. Beryllium plus an electron is up here. Well, let's take an electron, let's add an electron. We took one off and it cost me energy. Let's put one on. Let's say take beryllium and put one on and go to beryllium minus. That is also endothermic. So to go anywhere from this state requires energy. This is the one that's stable. All we're saying is that's low energy. It's not magical. There's nothing magical about this itself. Closed shell, that's BS. All we're saying is it's lower energy than to take an electron on or take one off or put it on. So I hate that magical closed shell. It's closed, magically stable. Well, what? Stable? I hate that word. Oh, sorry. That's my phone. Sorry, I have to keep that on. My mom's in the hospital. It wasn't the hospital. That's what I checked. Continuing back to that. So that's beautiful. Right back to the first day of Chem 1 and all the work we put in to understand quantum mechanics and what's going on. It comes back to do this beautiful thing that you maybe remember from your last chemistry class: closed shells are stable. And now you understand why quantum mechanically, because you understand ionization energy, structures of atoms. That's a beautiful thing. I just want to pause and just soak that in for a minute. Okay, here are some other ones. You notice, same thing happens, these closed shells. Okay, half-filled shell. People say half-filled shell is stable. Well, it is, because it doesn't really want to go accept an electron, and taking one off is hard. The fully closed shell, yes, stable, because the other things take energy to go to, or at least aren't any better. Brilliant. Okay, let's plot them out. You know that I love doing that kind of crap. So here they are, plotted out, ionization energies. And we understand as I go across the periodic table, I'm going across a row, I expect ionization energies to increase. And there they go, increasing as I add an electron and add a proton, and all the way up to here where I'm at neon, and then suddenly at neon, it's easier to ionize dramatically sodium, and we understand why that is. Because this is in the principal quantum level 3 and shielded by all these electrons below it, so very low effective nuclear charge on that 3s. And that's why, going down the column, we see ionization energies decrease. And there we go, across the periodic table. And notice it's not perfectly going up, but we understand why. Oh, and here's very important. So if I'm going up here and saying ionization energies are going up, but that means the relative energies of these species are going down. Remember, high ionization energy, let's do it dramatically here. If your ionization energy is bigger, so if you both have to go to the 0 state, if your ionization energy is bigger than something else, you are actually lower in energy than that thing, because this is the energy you're talking about. So it's 3p here, or 2p, is lower in energy than 2p4, because the ionization energy, is what I'm plotting here, is higher. Okay? Write that out on your own. That it's a little confusing, right? So write it out, and so you convince yourself of this. Because I'm going to draw that picture, and I'm going to draw that picture and ask you which is the higher ionization energy. You don't want to say that one. That has the higher in energy, but it has the lower ionization energy. Okay? And we know why this is the case. Sure. We have this P3. Where is P3? You go P1, P2, P3, and you get to nitrogen. And nitrogen, slightly lower in energy than this, and this one here, even easier to ionize. This is great exam stuff. Where do I put this one relative to those two? Well, it's even easier to ionize. 2p2 is here, even easier to ionize. There they are. And there's what you see. This is stable because everywhere else is higher in energy. Okay? Lovely. I don't know about you guys, but I am, I wonder what this one is. Is this one blowing stuff up? No, it's just a periodic table. Dull. That's probably just this picture on a periodic table. Okay? Okay, so we can start doing this next time. This is pretty straightforward. We got 2 minutes. I don't think this is very compelling. It's a periodic trend. Which is the smallest radius? And you look at their positions on the periodic table. And you would look at their positions on the periodic table, and you would do that. But before you go, everybody is logged on to EduRoam, I hope. Let's tell me you are here. I'm going to turn the microphone off. Okay, there is a little bit of a hole in the system, isn't there? Before I ask you to enter Barbie, there's another hole in the system because I just said it. But I think I'll turn off the poll. I shouldn't tell you what the hole in the system is because some people might not have realized what it is. What we're trying to do, as you know, is we're just trying to see who's in the room. And we want to give you attendance credit, but we don't want to give you attendance credit for physically sitting here. I don't care about that. The whole idea is to use your poll everywhere. If you're using your poll everywhere, you're talking to the people around you. I want to give you credit for being here and talking to the people around you, not physically sitting here. So that's why we're trying to do this in a way that seems somewhat painful. But that's just because poll everywhere won't tell us who's in the room and who's not in the room. Okay, we'll see you tomorrow morning.